Week 9 analysis of frames and machines, right? So we'll determine support, reactions, and internal forces of frames and machines by solving equilibrium equations. So that is kind of extension of truss analysis we did before. So I have very short slide today. So this is typical example of frame. This is typical example of machine, right? And then we will apply the equilibrium equations following these steps. So we plot the free body diagram, including support reactions for frames, if there are any. And then for machines, we don't have any supports. We have connections, though, right? So, and then make a cut if necessary. And then for these two systems, we have multiple parts. So we must cut. So it is two-step procedure. First step is global analysis. We analyze as entire structure, solving 3 equilibrium equations. And then step 2 is local analysis. We cut sections, section by section, and then think about the equilibrium of each section. So for this, and then this. For this one, this problem you will solve during your discussion section. And then you will dissect every single part. And then to calculate the force on this wire to cut this wire, right? So that's machine analysis. Okay, and then for a cut section or a cut joint, dissected joint, set up equilibrium equations. So this method of joint, we use only force equations. Method of section, we use all 3 equations. Typically, you will use method of section for this equations, these problems, and then check final answer whether your answer is reasonable based on your engineering judgment, right? So that's the procedure, and then procedure, final, free body diagram, step 1, global, step 2, local, and then check your answer, okay? Okay, then this is the only clicker quiz today, so I'll give you a little more time to complete. So for this problem, which equation is not correct? And let's see. So there are 2 frames, and the C, pin, B, F are also pin. And let's start the clicker quiz. And then, first one is moment at C equals 0, moment at F equals to 0, and then sum of just Bx plus Fx equal to 0, By plus Fy equals to 0. Which one is not correct? So feel free to discuss with your peers, and then I'll give you 1.5 minutes. Yeah. So I close after 10 seconds. Yep. Okay, everyone, right? Yep. Okay, so this is the result, and D has the most vote, but some chose A, B, C. So let's check it together. So what about C and F? C is here, right? C is hinge. So at hinge, is moment 0 or non-zero? At pin, moment should be 0, right? It's pin. So I told you that think about a thumbtack, right? And then this thumbtack, so this plate, if we use thumbtack here, can this plate rotate? Yes, so because it can rotate, there's no movement, right? So C is a pin, F is a pin, so both A, B are correct. And then C, Bx is this, Fx is this, so C is sum of Fx equals to 0, right? So this is correct. And then this is Fy equation. And then when we look at this structure, we have By, Fy, and then 48 downward. So D is not correct. And then to make it correct, we need to add minus 48, right? Here. Then this equation will be correct. Okay, any questions? So for machines and frames, you will use this Fx equation, Fy equation, and moment equation. So the first problem is frame here. So for the frame and loading show, determine the force acting on the member A, B, C here at B and at C. Okay, so it's typical frame problem, and then we have these two members joining together with this pin. And then, yeah, second problem is typical. Okay, C and D are pins, right? So start with the global analysis. We need to try to find the reaction at C and D using global analysis, but C is pin and the D is pin. How many reactions do we have for a pin? 1, 2, 3? 2, yes, thank you. So then we can add Cx, Cy here, and dx and dy here. So we have 4 reactions, 4 unknowns. Okay, then in step 1, we will use entire, so global equilibrium equations, and we have only 3 equilibrium equations. So what we need to think about is, we may not be able to solve all these 4 unknowns using global analysis, right? But we should have some equations from step 1. So let's try with moment equilibrium equation. You can use either C or D because each point has 2 reactions, right? So, and I think the external force here is 200 Newton is aligned with D. So if we use D, then we can eliminate moment from D as well. So I can use D. And the D is now our reference point, and assuming one direction is positive, and we can count all the moment together. So here, moment by dx and dy, 0. Moment by 200, 0. And moment by cy times 90 or 120? 120, yes. And then moment by cx times 90, perpendicular distance, right? And then it's negative. So we had one equation about Cx and Cy. We cannot solve it, although this is moment equilibrium equation, right? Okay. And then we can have 2 more equations. So Cx and then Cy, right? So let's write it down just for our information, because it's first problem we solve for frame. If right side is positive, then what do we have? Cx, right? Dx, right? 200, right? So if you see something like this, then, wow, make this equation 0, make this equation satisfied. Some of this must be negative, right? So that's what you need to think about, okay? And then Fy equation, we have Cy and then dy upward. So Cy plus dy equals to 0. And then when you look at this equation, what does it mean? Cy and dy with same magnitude in the opposite direction, right? So, okay. Then now we have 3 equations, but we cannot solve anything, right? So that's why we need this step 2, make a cut and analyze the local member. So for frames, we typically cut at the joint here, B, and then dissect each local member, either this upper L section or lower L section. And then which local member should we use? That's based on what's asking in the problem. So here, problem asks us to find the forces at B and C. So B is here, and then C is here. Okay, which member should we use? Upper or lower? Upper, right? Because upper member has B and C, right? And then when you solve this one, then we can find the final answer, right? So let's plot the upper member. Okay, and then this is B, this is C, right? And then at A, we have 200 Newton. And then B is a pin, right? So we can add 2 forces, 2 independent forces, X, Fx, and then Fy at B. So I'll use Bx. Oh, it's not inclined. So it's Bx, and then By. Because I don't know the direction, I just use positive direction. And then the last point is C, right? And then C, we assumed Cx here and then Cy here. And global free body diagram and the local free body diagram should be consistent. So we should use the same direction. So these 5 forces are all forces on this local member. And then now we need to add the dimension here. So between A and B is 120 millimeters. Between B and C, we have 120, so 240 millimeters. And then between A and C, vertical distance here is 90. Okay, so this is the local free body diagram, so I'll just show you this. And then for each cut section or each member of the frame, we can set up 3 cooling equations: moment, Fx, and Fy. So let's set up those equations accordingly. Okay, so here, which point could be reference point for us? So I'll show you everything here. I heard C, B, C. Either points are great points, right? Because each one has 2 reactions, right? B is a good point, C is a good point. And I want to try B because we have one equation about Cx and Cy, right? So if we use this point, then we can have additional equation about Cx and Cy, then we can find Cx and Cy right away, right? So that reason, I'll use B as a reference point and then set up the moment equivalent equation. So for this, I'll give you about 2 minutes so that you can set up moment equivalent equation and then, yeah, compare it together. So let's compare together. So B is reference point, so moment by Bx and By is 0. Moment by 200 times 90. And then moment by Cx, 0, yes. And then moment by Cy times 240, yes, 240. And then, yep, plus, yep. Okay. Okay, then now, what is Cy? Negative 75, that's what he has. And I have 2 Newton. Okay, so Cy was found as minus 75 Newton. And then now we can plug this into the first equation and find Cx, right? What is Cx? Cy, so 120 times Cy divided by 90, right? So that's minus 75 times 120 divided by 90, right? So it's minus 100. So what we have Cx minus 100, Cy minus 75 Newton. Okay. Any questions so far? So using this 2-step method, we found Cx and Cy. And what else should we need to find? So it's Bx and By, right? Then we have this local structure. So by solving Fx equation, we can find Bx, right? What's Fx equation? We have Bx, Cx, and then 200. And here we found Cx is minus 100. So Bx is also minus 100. Minus 100, 200, 0, right? And then last equation, Fy, if upward is positive, we have By, Cy, that's all. And then we found Cy minus 75, so By should be minus Cy, so 75 Newton. Yep. Okay, so these are the answer. So if you see this kind of frame problem, then remember to have at least 2-step procedure, because typically you have more than 3 unknowns for frame analysis because it's frame. So typically either supports are hinges or pins, right? Then you need to cut and analyze the local member. Okay. Any questions? Okay, move on to machine analysis. Yeah, very lengthy problem statement, but we can simplify and then solve this problem. I know there are many mechanical engineers, so very excited, right? So the cab and motor, so let's see. Yep. The cab and motor units of the front end loader shown are connected by a vertical pin located 2 meters behind the cab wheels. Okay, so this is loader, right? It's bucket, and then this is cab wheel, right? And then this is the engine, right? So distance from C to D is 1 meter. So C is here, D is here. Oh, okay, so distance between C and D is 1 meter. And center of gravity of the 300 kilonewton motor unit is located at G sub M. Where is this? G sub M. So it's motor unit's weight, right? And then while the center of gravity of the 100 kilonewton cap and 75 kilonewton load are located respectively at G sub C and G sub L. So G sub C is here, cap, and then G sub L is here, loader, right? And then knowing that the machine is at rest, that's important. So this is statics, so everything should be at rest, equilibrium. With its brakes released. Brakes are released. What does that mean? We have 2 rows of wheels. Brakes are released. So what kind of support should we use? Roller pin fixed? Roller. Brakes are released, right? It can move, right? So 2 rollers, okay? And then we need to determine the reactions at each of the 4 wheels. Okay, so that is kind of tricky part, right? So we only see these 2 wheels, but typically we have 2 wheels per, right? So think about this 2, right? 2 wheels. And then forces exerted on the motor unit at C and D. Oh, C and D here. Okay. And it is exerted on the motor unit, so motor unit is here. So we should cut this and then think about the right side section. So the problem is giving us very specific instruction. We need to cut here and then consider this section and then find the force at C and D. And then what is CD? So that is vertical pin. What is vertical pin? So vertical pin, something like this, right? So there are some holes here, right? And then there's a one member like this, and then it's connecting that C and D, right? So the one member here, right? But there are 2 connecting holes, right? Right? And then we need to find the forces at C and D. Okay, so that is very lengthy problem statement. Okay, and how can we solve this problem? We need to simplify. How can we simplify? How can we simplify? So I will use extreme simplification for this machine problem, and I just use one beam or one linear element like this. I deleted everything. It's machine, I'm sorry, it's machine, but just member, linear member. And then C and D, so that's vertical pin, right? So I'll use internal pin as CD. And then at the wheel, they are rollers, so that's our conclusion. So I use rollers at A and B. So it should be unstable, but we didn't include any screw or bolted connections and rigid parts in the machine. So this is fine, okay? Yep. And then, so this is my simplification. Very extreme simplification, right? And then now let's add some forces. So we have 75 here. And then at A, it's roller, so we should have only one reaction perpendicular to the surface, right? And it's okay to have AY as is, but sometimes we forget the original statement. And then the original statement, they ask us to find reaction at each of the four wheels. So I recommend using 2 A's so that you can find AY, and that's the final answer. And then now we have 100 kilonewton here, so 100 kilonewton. And this is global free body diagram, so I will not add any internal forces at here, CD. And then B is roller, so same thing, 2 BY. And the last force, 300, the weight of the motor. 300 kilonewton. Okay, still confused, right? And now let's add the dimension. So between 75 and A is 3.2, right? And then between A and 100, it's 1.2. And then between A and CD is 2. Right? So I'm just using the dimension given here. So between CD and B, 2.8. And between B and the G sub M, 0.8. Okay, and then now let's not think about the original plot and then just use this. Okay, and then this is A, this is B, and then this is C and D, right? Then it's machine analysis, so we'll do two-step analysis. So step 1 is global analysis. We need to find AY and BY by solving equilibrium equation, and machines are typically unstable based on our deterministic stability standpoint, but it is totally fine because there are so many other mechanisms internally. So, okay. So, but equations we have are the same. Moment, force X, force Y, okay? So, moment equilibrium equation. And which point would you use for the reference? We have only two choices, A or B. Either point is fine, yeah? So if we use A, and assuming one direction is positive, right? Then A is the reference point, and we count for all the moment contribution from the forces. So now 75 times 3.2, so that is moment by 75, right? And then moment by 100, 100 times 1.2, and then 2 by times moment arm 4.8, great. And then 300. Thank you. 4.8 plus 0.8, 5.6. Right? So this is the equation. And then that's all for BY. B1 189, 185. Anything else? 187.5. Maybe I like 189, 187.5. Anything else? I got something different, that's why I'm asking. 168. Yes. 162.5. 160. Yeah, so that's second. And then there could be minor calculation errors, so that's fine. Yep, so, but I like to know how many different answers you got. Yes. 162.5, so 3 votes. Okay. I got 162.5 as well. Yeah, so 162.5. Okay. So BY is 162.5. So this point, these times 2 are acting on this roller. And then the remainder is AY. Of course, we will solve FY equation. Upward is positive, then we have 2AY, and all others are known, right? So anyone who got AY? 70, 75. Okay, so that's what I got too. So 75, yep. So good. Now we found the first part, right? So where's first part? Reactions at each of the 4 wheels. So here there are 2 wheels here, 2 wheels here, and then AY, so front wheel 75, and the rear wheel 162.5. Does it make sense? Yeah, motor unit is more, weight, has more weight, right? So BY should be much higher, okay? And then second point, the force is exerted on the motor unit at C and D. So that's tricky. And then that needs step 2, local analysis. And we need to cut at C and D. So for you, if you have space, and then try to plot this one, or just use my note, okay? And I prepared this one by word processing. And then just cut here, and then I use this motor unit, okay? Okay, then it's okay to use this one because we already simplified a lot, extreme simplified, so we now can see this one is just 1 bar, right? And we have 300 kilonewton here at GM here, and then we know the distances, and then also we know 2BA, so that's 2 times 162.5, right? So that's 2BA, and then now what kind of force do we need to define? So that is the problem, okay? So this vertical pin, okay, vertical pin, but it is 1 member, so like this pen, 1 member, and then it is connected on top side and then the bottom side like this, right? And then whatever the vertical force right here, is this vertical force at these 2 points the same or different? One member, internal force of this, right? This 1 member, should be the same. So that is the key. Then we can eliminate that. So let's see. So something like this. It's the same force acting here, right? And then let's use this as CDY. One force at the vertical pin. What about the horizontal forces, horizontal reactions at here and here? Equal to 0. Yep, good inspiration. Yep. But yeah, maybe we can say Cx and then Cy, dx, something like this. We can define two different reactions or forces at C and D, and then you already know that. So C and D could be same magnitude in different direction or something like that, right? So that's a very good point. But for the free body diagram, we can define these two unknown forces in horizontal direction because there are two connection, right? And then for the vertical, we need to define only one because one member, okay? Then now we are ready to solve the equilibrium equation. Any questions? So defining this is the most important thing here, okay? And then solving, it's fine. So we have moment, fx, and fy, right? So moment equation first. And we have two choices, cx and dx. You can choose any point. Yep. But I would use D. It's totally fine to use C because anyway, moment from this is 0. Okay. Okay. Then if counterclockwise is positive, then we have Cx times distance between C and D is 1. So just Cx is fine, or I use 1. Okay. It's written in the problem statement. 1. I didn't make. And then moment by 300. 300 times distance between this to this. 2.8 plus 0.8. 3.6. And then last moment by 2by. 2by times distance here, 2.8. Yes, thank you. And you see two variables, but we already calculated by, and then there's 162.5. So we can find Cx. Minus 170, right? Kilonewtons? Kilonewtons, yes. Thank you. So I was confused. Okay. So did you get this number, minus 170 Newton? No? Okay. So maybe you can move this one to here, right? Then 2 times 162.5 times 2.8 minus 300 times 3.6. Right, so that's minus 170, so that's what I've got. Okay. Okay, then what else do we need to calculate? Dx and then CDY. So we can subsequently solve fx and then fy equation, right? So fx equation, all the horizontal forces, cx, dx. So you are totally right, cx and dx, the same magnitude and different direction. So 170 kilonewton. And the last equation, fx, fy equation. So c dy is the only unknown, and we have 2by minus 300. And again, by is 162.5, so c dy is 162.5 times 2 minus 300, right? And minus, right? So minus 25 kilonewton. Okay, so when you saw the problem statement, maybe you were overwhelmed because there are so many things, but it's important to simplify the overall structure to find, and also define the role of support here. Solve step 1, step 2 to find the reactions.